I'm going to talk about a new notion of kernelization for counting problems. I'm Rav Zehavi, and this is a joint work with Daniel Okshanov, Pranabendu Misra, and Saket Saurav. So let's start with some background on kernelization. So here we deal with parameterized problems. This is simply means that each instance of the problem is associated with some parameter k. This can be the size of the solution that we are looking for. This can be some structural measure of the input graph if we are talking about graphs. For example, it's vertex cover number, it's tree width, it can be the number of strings, the number of variables that we have in the input. The main notion for this talk is that of a kernelization algorithm, which is a pre-processing procedure for parameterized problems. Here, given an instance of the problem, so K denotes the parameter, we need to output an equivalent instance of the same problem in polynomial time. Okay, so far we didn't do anything interesting, but the point in a kernelization algorithm is that the size of the output instance should be bounded by a function only of k. Okay, so it can be that we get an instance that is huge, but if k is small, and assuming that f is reasonable, then we still get a small instance as an output. And we can also demand that the parameter itself does not increase. Okay, so this is a pre-processing procedure, and pre-processing is ubiquitous in almost every aspect in computation. If a problem has such a kernelization algorithm, then we say that it admits a kernel of size f of k. And a compression algorithm is more general. It is defined similarly, only that now the output instance can belong to a different problem than the input instance. This problem might not even be in NP. And in this case, we say that the problem admits a compression of size f of k. Okay, so I can look at this pictorially as follows. So previously we talked about a decision problem. So equivalence meant that if we have a yes instance, then we have a yes instance. If we have a no instance, then the output is a no instance. But this is also good for optimization. So instead of equivalence, we will demand the following. So given an instance of our problem, we want to be able in polynomial time to reduce it to another instance of the problem. This is what the reduce procedure does. And we want that the output will be small, bounded by a function only of the parameter. Now, given a solution, an optimal solution to the output instance, we want to be able to compute in polynomial time an optimal solution for the input instance, the instance we started this. This is what the lift procedure does. So we have two procedures, reduce, which takes us from the input instance to the output instance, and lift, which takes us from an optimal solution to the output instance to an optimal solution of the input instance. But this framework doesn't fit when we talk about approximation, and this is why in 2017, the framework of kernelization was extended to approximation problem as follows. So here, when we get an approximate solution to the output, then the objective of the lift procedure is to get also an approximate solution to the input instance. And furthermore, we allow to get an additional approximation factor of alpha. Okay, so when alpha is equal to 1, then in particular, this is a more complicated task than we had before, because now we don't just need to take an optimal solution to an optimal solution when beta is equal to 1, but for any beta approximate solution, we want to be able to lift it to a beta approximate solution. But even more generally, alpha can be greater than 1. So in particular, when we get the new instance, we want to solve it. And if it is a hard problem, then we might want to solve it using approximation algorithm. And then the previous definition is useless. Specifically, then we need to use this definition because we do get an approximate solution to the output instance. And compression is defined similarly. We just replace that demand that the output instance would belong to the same problem. Now it can belong to a different problem. So similarly, we also defined alpha approximate compression. So for upper bounds, there is a variety of techniques, and you can look descriptions of many of them also in the books. For lower bounds, we essentially have one main technique, which is the design of OR&N compositions. So I will define it now because it is also relevant to our contribution for counting problems later. So here we get t instances of some NP-hard problem A. And in polynomial time, we can compute an instance of some parameterized problem B, some instance yk of a parameterized problem, such that two conditions are satisfied. So first, if we talk about an OR composition, then we want that the new instance of the problem B will be a yes instance, if and only if at least one of the xi's is a yes instance. So we have OR, yk is yes if the OR of the xi's is yes. And furthermore, we want k to be bounded by a polynomial in the maximum size of a single instance among the xi's plus log t. So the parameter, notice it depends only on logarithm of the number of input instances. Now, if for a parameterized problem B, we can design such a reduction, then it is known that the problem B does not admit a polynomial compression. It is unlikely to admit a polynomial compression. Okay, so what is our framework? So we generalize this to counting problems. So here, instead of lifting an optimal solution to an optimal solution or an approximate solution to an approximate solution, we need to lift the number of solutions to the output instance to the number of solutions to the input instance. So reduce works in the same way as before, and lift now deals with number of solutions instead of the solutions themselves. So what was known before we defined this notion, what was used? So first there was an approach, in a sense, a hybrid approach, where we reduced the counting problem to an enumeration problem, where the solution set can be partitioned so that each solution to the input corresponds to one of the parts that we got for the solution sets of the output. Also very similar to one, we can just directly deal with enumeration problems. So we had a notion of kernelization where the input problem is also an enumeration problem. And the third framework is that of a compactor. Here, the lift procedure, it is termed a bit differently in the paper that introduced this framework. So the lift procedure, which takes the number of solutions in the output to the number of solutions in the input, it can run in exponential time or worse, and it also cannot look at the input instance. So this is not really in the spirit of kernelization, where the preprocessing, all aspects of the preprocessing should be extremely efficient, specifically in polynomial time. So there was no natural definition for kernelization for counting problems that it's similar to kernelization itself, or at least kernelization for approximation. In parallel to our work, there was another framework that was introduced. So here the number of solutions in the input and output instances must be equal. So this is more in the spirit of our definition, but it is extremely restrictive. And to demand that the numbers of solutions exactly will be the same, while we still want that the output instance will be substantially smaller than the input one, bounded by a function of a parameter. And furthermore, in none of these previous framework, there were known any non-trivial lower bounds. So to accompany our definition, we also have a framework to prove lower bounds. So first, we define the notion of an exact composition. So here we take t instances of a Sharpie hard problem A, and in polynomial time we have we need to produce an instance of our counting problem B. So the first condition is now replaced by that if we have the answer to yk, then we can compute the answers to all of the xi's in polynomial time. And furthermore, we demand, like before, that the parameter k is bounded by a polynomial in the maximum instance size among the xi's plus log t. And so we prove in the paper, and this is quite similar to the previous proof, that this means that the problem B does not admit a polynomial compression using our definition. It is unlikely to admit a polynomial compression. We also defined what we call a sum composition. So here we do not demand that we can compute the answers to the xi's using the answer to y, but something quicker. We just demand that the sum of the answers to the xi's equals the answer to yk. It is weaker in the sense that it is easier to design reductions to show hardness using this definition. But unfortunately, we cannot prove a theorem like before using some compositions, and we just conjecture that if a problem admits a sum composition, then it is unlikely to have a polynomial compression. And it remains open to prove or refute this conjecture. Okay, so now let's go to the third part of the talk. So what did we prove using our new framework? So first, in terms of upper bounds, first we considered the counting version of the vertex cover problem, since this is the most well-studied problem in parameterized complexity, and also it is an easy problem in a sense. So we proved that this problem parameterized by solution size. So we ask whether there is we want to count the number of vertex covers of size at most k, and the parameter is k. So it admits a polynomial kernel. So now for a more broader class of problems, we proved that any problem in that class admits a polynomial compression. So this is the class of planar F deletion. So here for us, a solution is a set of at most k vertices, such that when we delete them from the graph, it doesn't have any graph from F as a minor. So this is more general than vertex cover. Specifically, we only consider the case where the family F contains at least one planar graph. So this is a very general class of problems that includes vertex cover, feedback vertex set, deletion to some specific tree width, and more. Okay, now in terms of lower bounds, so first we use the exact composition for which we have the theorem and not just a conjecture. So using the exact composition, we showed that mean ST cuts. So we need to count the number of mean ST cuts in the input graph, parameterized by the tree width of the input graph, does not admit a polynomial compression. This is interesting because For the decision problem, this is solvable in polynomial time. And also it is FPT by 3-width. The counting version is FPT by 3-width. And using some composition for which we only have the conjecture, we were able to prove several lower bounds. So we proved that we don't have a polynomial compression for mean ST cut where the parameter is the mean cut size. For odd cycle transversal, where the set that we need to remove is such that the graph that remains does not have an odd cycle. So this problem, the decision version has a polynomial kernel, and the counting version is FPT, but this does not have, the counting version doesn't have a polynomial compression even parameterized by solution size. And also for vertex cover parameterized by the difference between the solution size and the max matching size. So again, for all of these problems, the decision versions have a polynomial kernel. And here we show that, or they are even in P, and here we show that they don't have the counting version doesn't have a polynomial kernel or even a polynomial compression. Okay, so thank you for your attention.